So this problem is going to use what is called as multiple step synthesis in organic chemistry, where you're going to mix and match and combine several reactions you have seen, and those reactions don't necessarily have to be part of just one chapter. You can always mix and match reactions from different chapters, which means reactivities of different functional groups. So in this question, you're asked to combine a nucleophilic substitution reaction with catalytic hydrogenation to synthesize the compound we're looking at. So nucleophilic substitution reaction, as you know, is something that is going to have a leaving group on a substrate, a nucleophile donating electron to form a carbon nucleophile bond, the leaving group gone. So that is a nucleophilic substitution reaction. And a catalytic hydrogenation is you taking an alkene, reacting it with a hydrogen in the presence of a catalyst to form an alkane. And a catalytic hydrogenation could also mean an alkyne using the same reaction, hydrogen and catalyst, to make an alkane, or it can even mean an alkyne reacting with a poisoned catalyst with hydrogen to produce an alkene, not going all the way to the alkane. So all these are catalytic hydrogenations. So essentially you're adding a hydrogen molecule or two to an alkene or an alkyne, and depending on whether it's a poisoned catalyst or an unpoisoned catalyst, you'll be able to get an alkene or an alkane. So these are all hydrogenation reactions. So we are going to use a combination of these reactions to get the product we are asked to make here. So in the first case, we are supposed to make cis 3-heptene. So we should make 2, 3, 4, 5, 6. So 1, 2, 3. On the third carbon, you want to have a cis alkene. 1, 2, 3, 4, 5, 6, 7. We are supposed to make this from butane. So 2, 3, 4. That's an alkyne, and bromopropane. So 2, 3. Bromopropane. So this is 1, 2, 3. That's bromopropane. 1, 2, 3, 4. That's butane. So we should try to make this compound, the product from here, not just with one reaction, but through a series of reactions if needed. And this is what you call multiple step synthesis. So as you could see, in the product we have 1, 2, 3, 4, 5, 6, 7 carbons, and the two reactions that are given here has 4 and 3. So we should try to make a bond between these two carbon containing molecules to get a 7 carbon structure, and we should not have just a triple bond, we should have a double bond. So we just saw a reaction in the earlier problem, how to combine two different carbon ends of a molecule. So if you take this alkyne and you treat this with sodamide in liquid ammonia, then you're going to get the acetylide as the product in this step. So you're going to make sodium acetylide Na+, and you're going to make an ammonia in this reaction as the byproduct. And after this is formed, you treat this with the alkyl halide, so the 3 carbon containing structure. So let's call this 1 prime, 2 prime, and 3 prime, or let's call this A, B, and C. Makes it easier that way. So you'll be getting 1, 2, 3, 4, and then A, B, and C. So A, B, and C. 3 carbons are here. 1, 2, 3, 4. 4 carbons are here. Therefore, it's going to be a butane structure. And now that we have understood how the carbon-carbon bonds are here, we can now just go ahead and label this 1 through 7 so that we know how to make this compound go to the final product structure here. So this is carbon 1, 2, 3, 4, 5, 6, and 7. So we have a 7 carbon structure, except that we have an alkyne on the third carbon and not an alkene. So if we want to go from an alkyne to an alkene, we need to use what is called as the Lindlar's catalyst. and this is something that again we discussed in chapter 3, and this is the poisoned palladium catalyst. Okay, so usually you just add palladium and hydrogen to an alkyne, and the alkyne will go to an alkene, then it'll go to an alkane, because the palladium is a very strong reducing agent, so it reduces all the way to an alkane. Whereas when you poison the Lindlar's catalyst with other chemical additives, you don't have to worry about that for this class, but you just need to know that the Lindlar's catalyst is a poisoned palladium catalyst. So when it is poisoned in the presence of hydrogen, it is going to go from an alkyne to an alkene, and it will not go any further, and the alkene is going to be a cis alkene. So that's what you need to remember. So this is the Lindlar's reagent, again something that we have discussed, so make sure you understand how the reaction works, read about this, go back and visit the problems we have solved. So alkyne Lindlar's catalyst is going to give you the cis alkene, and it is not going to go to the alkane, and since we want a cis alkene here, this is the final reaction that you want to give. So you start with an with an alkyne, form an acetylide, then react that with the alkyl halide, which is that, to give you the alkyne, and now reduce that with the Lindlar's reagent, which is a controlled reduction, to give you the cis product of what you're supposed to make. So the second part of the problem also is going to use, or the second problem is also going to use the combination of substitution and reduction reaction, or catalytic hydrogenation reaction, to get the product you're looking for. So you should try to make propanol, 1 propanol, from 3 bromopropene, from that. So if we call this, label this 1, 2 and 3, in this structure it's also 1, 2 and 3. Remember, this is not the way we would name it if you are trying to provide a systematic name for this compound, or number this if you're trying to make a systematic name for this compound, but this is numbering is only for sake of reference. So carbon 1, 2 and 3, carbon 1, 2 and 3, 1 and 2 has lost its double bond, carbon 3 is going to get a hydroxy where the bromine was. So we can first try to replace the bromine with a hydroxide. So we can react this with sodium hydroxide, and we'll have a substitution reaction, and that is going to give rise to the alcohol, as we see here. And once you form the alcohol, we can now simply treat this with hydrogen and palladium. It doesn't have to be a Lindlar's catalyst, because we are just trying to get the alkane directly, and the alkane cannot be reduced any further. So a regular hydrogenation reaction, catalytic hydrogenation reaction, will work, and that is going to be the product we get. So this is a substitution reaction, this is a catalytic hydrogenation reaction. In fact, you can mix and swap the reactions, and you can still get the same product. So if you just try to treat this with hydrogen and palladium, you will get the corresponding reduced alkane, as alkyl halide as the product. And now we can treat this with sodium hydroxide, and that will give the same product. So therefore both reactions are going to be able to produce the product you are looking for. And in organic chemistry, sometimes it works out the way that we have here, like which reaction you use first does not matter, you will end up getting the same product. Whereas there are reactions where the sequence of reaction steps are going to be very important, like especially when we saw in case of electrophilic aromatic substitution reaction, where an existing group that you put first can decide which way the second group is going to go, whether or not it's going to be an ortho or a para-directing group, right? So sometimes it works out fine, sometimes you have to be really careful about deciding which reaction to choose first.